My name's Evan Deutsch, and I'm going to be giving a high-level overview of the role that driving functions plays on the Wisconsin autonomous team. Um, I'm assuming that anyone listening to this has some general background knowledge of how the Wisconsin autonomous team is structured and how it operates. And I'm going to be focusing mainly on the role that driving functions plays for Wisconsin autonomous as a whole. So without further ado, I'll get right into it. The best way that I like to basically explain how driving functions plays a role in this team and what the different types of algorithms we run are and how they work is by kind of breaking it down into an input output type of situation. In this picture, driving functions is this block in the middle. I'm going to write df for driving functions. On the left is an arrow pointing in. Those will be our inputs, and I'll explain those in a minute. And then this arrow going out is going to be our outputs. I'll also be explaining that. And then in the middle, I'm going to explain the various ways that we can map from the inputs that we get to the outputs that we need to be giving out, and the different types of algorithms we use. And if you're on our team, you'll probably be using as well or creating. At the very least, you're going to want a background of all these different types of algorithms. So first off, as it goes with inputs, so I'm just going to put an I here to remind you that these are the inputs. The two main types of inputs that we can expect to get in as members of driving functions are information about the vehicle. So here's this. And then we also want to expect to get information about our environment. So the actual environment that our car will be essentially driving in. So given these two types of inputs, I'm going to basically explain specific types for each of them. But generally, these are the only two things that we need to really expect to get. Information about the vehicle will come from perception, but mostly that type of information will come from state estimation or various hardware teams, where we're essentially just reading off information that can be valuable to us. This information includes the speed of the vehicle, the velocity if you want the x and y values, the inertia, the angular velocity, the current position. So there's a bunch of different types of information about the car that we need to evaluate our algorithms. So I essentially am wrapping all that in under the name vehicle. So we're just getting all information about our current location and speed, etc. The environment includes a couple of different things. I'm going to write them down because they're a little bit less intuitive. Basically, the environment, we can expect to have information about the track. So I'll be explaining that more in depth in a second. But I think the track that we're racing on is essentially what we'll have information about. That's what I mean by track. Other things in the environment will be other cars. So opponents, I'm just going to write OPPO, but these essentially will be the other cars that we're racing against. It even could be obstacles. Honestly, this doesn't just have to be other cars. It could be, let's just put OBS for obstacles. It could be like a block in the middle of this track. It could be various other things. It depends on the competition that you're preparing for, but essentially whatever information we need about the opponents, about other obstacles, we'll be getting that information, and I'm pretty much grouping it under this environmental kind of tab. Other types of information will be like the coefficient of friction of the track. It might be the the banking of the track, other all those different types of information, gravity, which will be constant, but like we still have to kind of perceive that type of stuff. I'm just trying to give examples here, but if that all makes sense to you, these are the types of different things that I consider to be environmental. Either these will be given to you by the competition director, who's like, all right, we'll trust us, the coefficient of friction on the ground is 0.9 or something. Like, you won't need to be reading that in. But information about the track, the opponents, the obstacles, those have to be picked up in real time. And those will be picked up by the perception team, which, if you're familiar with Wisconsin Autonomous or basically any type of autonomous driving, is tasked with basically using LiDAR, other cameras, different technology to perceive our environment, see the tracks, see the opponents, and give us that information. By us, I mean driving functions, in the form of points, or in the form of essentially locations in a 2D field. So these are the inputs we'll have. You're going to get a little bit more familiar with them as I provide some examples for you guys, but essentially this is all you really need to know for now. Now we can go to the outputs. So this is what driving functions is tasked with outputting to other teams so that we can basically help along with this very complex process of creating an autonomous vehicle from scratch. So what we're outputting is going to be two things, essentially. It's actually going to be three, but conceptually it's okay if you think about them as two. So the first thing is a steering angle. So when I say steering angle, I think the best way to kind of understand this is if you kind of picture that you're driving a car. So picture you're in front of a wheel, like you're a driver. Here's your wheel right here. You've got your car. Your eyes are the perception team. So you're trying to see, like maybe there's like a tree here. I don't know. Like you're trying to see all the different things in front of you. Trying not to hit anything. Trying to stay within the lines of the road. This is a bad road, but this is all just for an example. Essentially every single time step. And when I say the time step, that word can be confusing, especially for people who are new to this type of nomenclature. But when I say time step, I mean in terms of programming, I mean the quickest that your program can run. So say your algorithm is trying to output a steering angle every time step. That means as quickly as it can, it's trying to tell your car where to turn all the time. That's essentially what it means. And the difference between the first time it tells the car what to do, so say it tells the car to turn a little bit to the left. So if we do this picture, like say it tells it to turn a little to left, and then time steps are usually very small. So say 0.0001 seconds later, the algorithm now thinks the car should be turning a little bit to the right because maybe an obstacle was placed down, maybe there's a turn coming up, who knows. It'll provide a new steering angle, the car will turn, and that's how the car will drive. And when we're talking about this in terms of algorithms and programming and math, it can seem very complicated. It can seem unintuitive. The time steps seem very difficult to understand. But when you're thinking about this is why I want to think about it like you're driving the car. When you're driving the car, you're always turning. You're always turning it one way. If you pause, if you take a snapshot in time. So say you're driving your car, you're turning the steering wheel left and right, and you just take a snapshot in time and you pause. That whatever steering angle that you're currently holding the car at is the steering angle that you're essentially outputting at that time step. If you take another screenshot 0.0001 seconds later and the steering angle is different, that's your next output. And the algorithm is essentially doing the exact same thing. So in reality, the whole thing with the steering angle every time step is the same as driving a regular car for a human. But conceptually it can be a lot more difficult to understand, especially when I use complicated words like time step and algorithms and running and like, I don't know. It can be difficult for people to understand. So I hope that helps formalize the understanding of what when I say every time step, because I'm going to say that a lot. So essentially the outputs will be a steering angle, and then I'll put at every time step. So I'm going to put AET. So you guys can just kind of remember that that's what that means, at every time step. Another value will be the throttle. So exact same thing as the explanation before, but for speed or the gas pedal. Like when you're driving, you're not pressing the gas pedal differently every time. If you take a snapshot, that'll be your current throttle value at that time step. So I actually want it to be at time step. So ATS. I think that's better. So I'm gonna change this first one. Sorry, give me 1 second. But anyways, yeah. So that's essentially how that works. We also do the exact same thing. So we do steering, we do throttle, we also do braking, because you guys probably could have guessed that if going along with the example of driving a regular car yourself. You'll also have a brake pedal, and it's going to be a completely different value that's independent to the throttle. But sometimes we can get a value for the speed that we want our car to go, and we can kind of use an algorithm to turn that value into a throttle and a braking value in an optimal way, even better than a human kind of can conceptually try to match the correct speed with those two pedals. But anyways, this is kind of what we output, the exact same way as a normal human would. That's all you really need to understand for now. So right now, if you're taking away anything from what I've said so far, I want you to understand that as driving functions, we can expect our inputs to be the information about our vehicle vehicle, which is the location, velocities, angular velocity, accelerations, all those values, position, etc. We get information about the environment, so that'll be the track, which I'll explain a little bit more in a second. But it'll be the location of the barriers, essentially, location of an opponent, an obstacle, the information about the coefficient of friction of the track, gravity, all of that jazz. And then with all that information, we're looking to run algorithms that at every time step can output steering angles. So let's confirm that this is an angle. That's pretty important. And throttle and braking. So that's pretty much all you need to know so far. Now I'm going to explain kind of the two different schools of thought. So when you're thinking about controls, like controls for an autonomous vehicle, you got to think about as with safety, racing, speed, like there's just so many different factors to take in, so many different types of algorithms. It can be very overwhelming, and a lot of the times, eventually, if you're joining driving functions, we're going to want you guys to be eventually finding your own projects, taking it upon yourself to find what's interesting to you, and then maybe start working on that. So it can be very difficult to kind of search those murky waters for an algorithm when there's just such a large field of different types of things you can choose from. So I like to break our team, what our goals are, down to two specific schools of thought. So these are kind of two ways that I can map from these inputs to these outputs, and that's why I drew a line in the middle. I'm going to map out the algorithms right now. I'm going to use a lot of words that are going to be confusing at first, but I'm going to explain them, so just bear with me here. So the first one starts with global path planning. So I'm going to go GPP, global path planning. So that's going to be the first kind of technique, and I'm going to explain that in 1 second, so just hold off. But remember that this stands for global path planning. Next will be a path following algorithm. So once you've basically plan a global path, you'll be following it with a different algorithm. We'll also be explaining that in a second. And then some type of obstacle avoidance strategy. So obstacle avoidance. So these are the three different types of algorithms that can basically allow for a successful algorithm with this school of thought. So let me first kind of show you what I mean by these three different phrases, because they probably don't make, maybe besides obstacle avoidance, you're probably not really sure what all these mean. So first off, global path planning. What does that mean? First off, this is actually not an optimal way to explain it. Let me first draw a 2D grid. So we have this grid. Everyone's probably familiar with the 2D grid, XY axis, whatever. We can basically expect a track, which looks like this. So, I mean, a track can be look like anything, obviously, but let's just draw a really weird one. That's probably a really weird track, but whatever. I'm horrible at drawing tracks, but just for the sake of argument. Here's the track. Essentially, this is what it looks like. So this is actually, believe it or not, what we see after perception gives us the information. So normally in a competition, what will happen is the car will blindly kind of go back and forth and just trying to traverse the track. It won't be part of the race. It won't be anything that is counted for scoring or speed or anything. It's just so we can kind of learn the track, and we use our perception knowledge, which that's a totally different team separate from driving function, so I won't get too into the logistics. But essentially, perception is in charge with using technology to fit in artificial intelligence to basically figure out where the barriers are and then tell us in a 2D space. So going into the race, we can expect to know some like this type of track. We know that this is what the track looks like. Now what do we do? So a global path planning algorithm will take this, and it will essentially draw an algorithm to the best of our ability. So there's a few different strategies. There's actually a lot of different strategies, but I'm just going to explain a few simple ones. One idea is a shortest distance path. So a shortest distance path might look like this. It's going to work on trying to stay on the inside. It will cut off corners, though. That's wrong. Ignore that kind of blip, but it'll stay on the inside here, cut off that, cut off this, stay on the inside. And essentially, it's not perfect, but that's what you can kind of expect a shortest distance path to look like. It's exactly what it sounds like. We will use some optimization strategy to basically take this track and then find the shortest distance path that spans the track. So that's what that would kind of look like. Now another pretty common type of algorithm. Let me just erase this track really quick. Whoops, I didn't mean to erase the whole track, but that's okay. We can easily put that back in. Just give me 1 second. The second different type that's pretty common that I wanted to discuss would be, we'll make the track less complicated here, would be a minimum curvature path. So what a minimum curvature path does, exactly what it sounds like. It's another global path planning algorithm. There's a couple different ways to implement it, but essentially it will minimize for curvature. So instead of going all through the inside of the track, it's going to just focus on turning the least. So it will look something like this. Just the minimum amount that it can turn the whole track. So that's another different type of implementation. There's many other global path planning strategies, but those are just a few examples. And that's kind of the first part of our first strategy for mapping from these inputs that we laid out, vehicle and environment, to the steering, throttle, braking, every time step value. So that's what that is. Then let's just kind of continue on. I think I just realized something. I'm being kind of dumb here. It's every time step. For all those people who caught that earlier on, I know I did at every time step, so that's probably why I was AET before, and then I changed it to ATS. So for all those people laughing at me with those, yeah, that's not the smartest, but I hope that doesn't take away from any of the lesson at all. So that's how that kind of looks. Anyways, so once we have the global path, what do we do? So, I mean, I hope you can answer if you were paying attention. What does the PF stand for? It's path following. So let's just zoom into the track now. So once we got the global path, we can even plan that before the race starts. Now the race is going on. We're right here. This is our car. This is our location, and this is a zoomed in picture of the track. And we've already planned a global path, just like I kind of laid out before. So this is what the global path, let's say this was the global path that we're talking about. Now we have the global path. Great. How do we follow it? How do we drive it? Why is a global path useful to us? And the answer to that question is because we can write a path following algorithm. This is how there's a couple of different types of path following algorithms. I'm going to explain the general idea for it, and then I'm going to get a little bit more specific with the type of algorithm that we use. But basically, how a path following algorithm generally works is it obviously you can see that this car is right here is off the track to the left. Like it is off to the left. That is indisputably what's going on here. So using some type of algorithm, the job of the path follower is to notice. Oh my god, I'm really messing up the colors here. Hold on. The job of the path following algorithm is to notice that the car is off to the left, and to correct it. So how can we correct it? Let me explain one type of algorithm that we use. So the type of algorithm that we use currently, it's the one that we use for our testing, but we're implementing different other ones. I just think this one's the easiest one to explain, so I like using this one. Essentially how it works is it's called a PID. So let me just write that over here. PID. What does PID stand for? It stands for proportional. So I'm just going to write prop, but you can remember that. That's proportional, integral, like calculus, integral, and then derivative, okay? So those that's what it stands for. So what does that mean? Hopefully you'll be able to find out in a minute. The first thing the algorithm does is it looks straight ahead, and it looks at a point, some distance ahead. This distance, it kind of depends on your ability of your camera. Ideally, it would be kind of far ahead, not too far ahead. It doesn't really matter. We can just call this distance D. Actually, I don't want to call it D. The distance, we want to call this, this is essentially a vector, which is the most important thing to know. And this vector is called the sentinel. So let's write an S here for sentinel. Another vector that's drawn is here. So it's the same distance ahead, but it's on the track. And then we can draw this vector. This vector looks like this. So let's just erase this right here because I don't like that line. So this is the sentinel, like I said before. This is the target. So the target's the same distance as the sentinel ahead, but it's on the track. So essentially you subtract those vectors and you get this vector. You get the error. So this is the error vector right here. then using this error vector, we want to minimize this error. That's essentially how it works. We want to get our car back on the track. How can we minimize this error? We're essentially going to find the derivative of this error value. So we use the previous error values, which we keep track of. We already have this algorithm implemented. You can see it on our GitHub. If you have personal questions about how to follow along what I'm saying with our implementation, you can ask me whenever. If you're watching this, you probably know how to contact me. But essentially, you find the derivative of our error values, you find the integral of our error values, and you find the proportional of our error values, which is essentially just the length of this vector right here. So once you get those values, you essentially can the equation looks like this. It looks like P times we'll say EP, so plus I times EI plus, that's a horrible I, my bad guys. Sorry for my drawing, it's horrible. Plus D times ED, and essentially this EP, EI, and ED are the values that I just explained. It's the proportional error, which is just the length of this vector here, the integral of the error, the derivative of the error. These values are constants, the P, I, and D. These values can essentially be determined with a by essentially it's a process called tuning, and there's a couple different tuning strategies, but for simplicity's sake, you can literally just use guess and check, and then eventually you can get that this value is equal to the steering value that we want to output, and that's it. That's this value. So, oh my God, like here, full circle. So we just went from global path planning to path following, and now we got our steering value. How do we get the throttle value? Same idea, but instead of having the target be this vector right here and having the sentinel be this one, our target's going to be some speed that we think is optimal at that time step, and our sentinel will the equivalent of the sentinel will be our current speed, and then we'll just change the speed based on a throttle value using the same PID type strategy. And there you go. Now you got the throttle. You can use the whatever you get for that value to help you get the braking, and you're done. That's it. So we finished. Like that's how you map from there to there. I hope that all made sense. Now you might be asking, okay, we get it. That's it. What's the point of this obstacle avoidance strategy here? And I'll explain it right now. Let's go back to our zoomed in picture. Say there was a car right here, and this is totally reasonable. There's a car driving right in front of us. They're right here, smack dab in the middle of our global path. Now, what do? That's a good question. It's actually a pretty difficult question to answer. That's why we got a whole topic reserved to it. Well, we can't just stay on our path because our path is blocked, and we do not want to crash. That's competition over all the time we spent on building our car, everything. We don't want to crash, so we can't let our car continue on its current path. We're going to have to divert from it. One strategy could be just kind of noticing that this is where the edge of the car is and just drawing a path that misses it. There's a bunch of different strategies, but essentially we need some type of obstacle avoidance method here if we want to make sure that we can avoid the tracks or the other cars. So there you go. That's the obstacle avoidance part. Now you guys understand the entire first implementation for our strategy of mapping from the inputs of the vehicle, the environment, and the those inputs to the outputs of steering angle at every time step. Because, by the way, our path, that path follower algorithm that I showed you, the PID, or there can be many types that do the exact same thing. Those are running every single time step. That's why we had to zoom in and take kind of like a picture of where the car was in time. Because those algorithms run very fast, repeatedly, over the entire race. And yeah, that's pretty much how they work. So I hope that makes sense to you guys. I hope you guys have a good understanding of how all this kind of comes together. And you guys just kind of can make sense of all the information that I just gave you. I know it was a lot all at once, but I think that laying it out this way is important. You can obviously rewatch this video. I want you guys coming to meetings after you watch this video, asking me questions, or if there's another sub-team leader ask for driving functions at the time of this, ask them questions. It's very important that you guys get these kind of concepts down before you get started. And yeah, there's a couple different ways we work with tracks and paths. For example, when I say a path, you see that line going across the track, you might be like, Okay, how am I supposed to create that line? What is that line? All it is an array of points. We also have a class on our control stack where essentially the input to that class is an array of points. So say we got a 2D grid like this, and you have these points. Obviously, they have x and y coordinates, but I don't want to show them. So I don't want to make them all bigger. Just you guys can see this, right? I mean, I'm not talking to anyone. I'm recording this, but so say whatever. Say we have all these points. They see how it kind of looks like a track. That's one picture. Let's take another one where we just have like kind of like a line of points. Like I said, this is all being done in the 2D plane, so you're definitely more than allowed to visualize like this. So essentially, the one on the right is kind of like a traditional path, what it might look like. You'll pass all these points into our path class, and you'll be able to have different functionality with that class. Some examples of functions are basically if you take a point, let's make that red so it's clear that's not part of the track. If you take a point here and input it into our calc closest point method of our path class, it'll essentially calculate this point because this is the closest point on the path to that position, and that allows you. That's part of the way that we do the sentinel target kind of that's how we calculate the target using the sentinel for the PID. So there's a pretty relevant example there, and essentially there's a bunch of other functionality. Another example is if you pass in let's do red again. If you pass in this location on the track, shoot, that's an eraser. If you pass in this location on the track, the algorithm can use a speed profiler to get the target speed at that point. And remember when I said with the PID, we use it for the throttle too. We find a target speed, and then that's how we get our target for the PID for the throttle. That target speed is found using the path class. It essentially uses an algorithm that kind of uses some physics of the car, and it tells you what the optimal speed, or not optimal, but like, yeah, the target optimal speed at this point in a path is, and then you can pass that into the PID and get the information that way. So that's why when I've been drawing the paths, they've looked like continuous lines, because that's totally allowed. But essentially they're arrays of points, and you can get extra functionality by using our path class. And lastly, on the left, you can see a track, at least how we're currently doing this. I'm pretty sure it's going to remain like this. It's essentially two paths. So each of them is literally a path. It has all the same functionality. A track has additional functionality where essentially if you get a point here, and again we have a track class that you can use. So this is what I'm referring to. If you take a point here, our track class can tell you that this point is outside of the track right now, so it's not in the track, and that way you can know not to put your car over there because it'll hit a wall. So if your algorithm's telling your car to go over to that point, that red point over there, that's no good. So that's essentially a general overview for how we utilize the track in the past that I've been explaining. So hopefully that makes it a little bit more intuitive and less kind of like, oh, here's a line that we have to figure out, like it's a little or a path, like it's not very clear. So hopefully that kind of clears up how our calculations work. And when you're calculating global paths, you're calculating arrays of points. So that's a big takeaway. I want you guys to remember that when you're calculating a path using like a global path planning strategy, you're actually just calculating an array of points. So remember that. And with that being done, we're almost done with this kind of lecture. We're gonna move on to the second school of thought that I like from when we're talking about map. Where did this arrow come from here? I don't know. Yeah, okay, we got that out of there. I don't know where that came from. Anyways, the second school of thought that I use to map from these inputs, vehicle, environment. I'm just repeating myself a lot because I want to like really drill this information down, and then mapping that to steering angle, throttle, braking at every time step. We use it, and this is a lot more. It's not more simple, but it's less information. It's called a local path planner, and the most general way to describe a local path planner is you get the best of both worlds. It uses all of these types of algorithms kind of all in one, and it might be kind of confusing at first how that works, but I'm gonna explain that right now. So let me just erase that. I haven't used the software before. If it's not clear, that's why I keep erasing all the boxes and everything. I probably redrawn that box like 4 times. But yeah. Anyways, let's do a little zoomed in kind of version again. It's we got our car, and what do we do? So this is our first time we're doing this. So this is during the race, and we have no idea where we are. We're kind of lost. We're not lost, but like we don't have the global path plan. We have the barriers of the track. We have those known because of perception. I told you they've given us the track already. We have that as input. Nothing's different here. We don't have a global path though. We have not created a global path. So essentially, how a local path planning algorithm works is it's going to plan its path every time step. So instead of just every time step following the global path that it has, it's just like it sounds. Locally, every time step, it will be also planning the path. So how it does this is it'll essentially it'll draw, well, there's a bunch of different strategies, but the most general way I can describe it, and the best ways to do this, I want to iterate this before I continue with this explanation, is the best ways to do this is it uses like a function, like a continuous function that can basically explain every single possible path that you can literally follow at all through like a given, like the next like 10 time steps. And that's how, and then it will try to optimize like that continuous function. But that's pretty high level. And you'll come to learn this as you learn those types of algorithms as you get more familiar with the information. So right now we're going to visualize in a slightly different way because it's impossible to draw like a function that can provide infinite paths and it's continuous. So we're going to draw a discrete version of this. And this discrete version, basically the car, as messy as this looks, it's going to basically draw, let's say, how many paths are here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It's like 12. So let's say we drew 12. The car's like, okay, I can take these 12 paths. These are all, and when I say paths, what's a path? If we were in our meeting here, I'd make you say an array of points. So it has 12 paths that it can follow. How does it choose? It basically arbitrarily chose them. It doesn't have to. Again, it can optimize a function and really choose the mathematically best solution. But in this case, we're trying to choose the mathematically best solution out of the given choices, which were basically arbitrarily chosen. So which of these paths is the best? Well, there's a few different types of strategies that you can use, and they might sound familiar. The shortest distance strategy, that'll be the one that goes straight ahead, just like this. The minimum curvature, and again, these are pretty short lines, so it's going to be kind of hard. I guess the minimum curvature would be that one. So let's reiterate that. The minimum curvature one will be the one that goes straight. The shortest distance, like it'll kind of depend. These lines are really, really short. I wish I'd kind of do them a little longer, but the shortest distance will probably look like this because it's going to want to try to, if you can picture the lines being a little bigger, do me a favor. The car is going to want to, like you saw with the global path planning techniques, it's going to want to stay toward the inside of the track. Like that's just how it's going to kind of work because that's the shortest route to forwards. Like if you want to get to like this point X, like you're not going to go up here and then around. That's not the shortest distance. So you can just, whenever you think shortest distance, you can kind of like think, you can expect it at least. If it doesn't, you might need to investigate, but you can expect the car to try to go toward the inside of the track. So essentially, the one on the left, I should not draw I should draw these different colors. This blue one's going to be shortest distance. But essentially the blue one's going to be shortest distance. The red one's going to be minimum curvature. You can also do various other types of algorithms like that that can work. You can combine these with some weighted function. This is up to our new members and our current members to figure out, find these new strategies. But generally, you're going to pick a path, and that's essentially how it's going to work. After you pick the path, in the same exact algorithm, you're going to essentially use a built-in type of path follower to essentially. So let's say we choose the shortest distance. I like the shortest distance in this example the best. So let's say we do this. Don't erase that. Perfect. Let's say we choose the shortest distance. We're essentially going to, inside the same algorithm, because this is all operating every time step, it's all like one. It's all in one. It's not really as separated as it was in the other strategy, but it's going to be similar principles still. You're going to look at this sentinel. I don't want it to be blue. You're going to look at this sentinel. You're going to look at this target. You're going to find the error. And you're going to tell the car to get on that path. So there you go. The local path planner will do that. It can use a built-in path follower. Some local path planners can derive, and instead of even, like, remember when I told you guys a second ago that you can use functions instead of arbitrary paths? If you use a function, you can optimize not even for the right path. It might be difficult to understand, but you can optimize for the control inputs, which are, so let me just map this because I just threw out the term anyways. These are all control inputs. That we're using a controller to get these inputs into the vehicle. I know there are outputs, so it might be a little confusing. There are outputs, but they're inputs into the vehicle, so we're going to call them control inputs. So we're essentially going to be so when you're doing the continuous function strategy and then optimizing for the best future path every time step, the best way to do that would probably be to optimize for steering angles and for throttle values, because that's just more efficient. But in terms of the arbitrary path, let's just kind of try to get back to where we were before. Let's see if I can stop erasing the track. But we'll go back to where we were before. We had the shortest distance path. That is horrible. Whatever, it's for argument's sake. That's our shortest distance path. In this strategy, instead of optimizing for, we're not optimizing for control inputs with as we would maybe with a continuous function. And if you don't understand that, it's okay. Like don't focus too much on that. We can do the same strategy. I already told you. I don't know why I'm repeating myself. Sentinel, target, and then the errors here. So there you go. That's how that works. And then you might be asking how obstacle avoidance is incorporated here. If we were to draw, let's restart this process really quick. This is the last thing. I know this video is getting a little bit long, and I just erased the path again, or the track, I mean. So let's say there's a vehicle right here in front of us, and we're using a local path planner. It's going to draw those same 12 paths that it did before, just like this. I'm not going to draw as many this time. Let's just cut it there. But what it will do is it will be like, all right, so we see this vehicle because perception tells us that's, again, one of our inputs. We see the vehicle, and we're like, all right, all these paths are going towards that vehicle. We can just nix them. We don't even need to test them. We don't even need to consider them. That's done. So what we'll end up doing is we'll be choosing between, we can't do red there. We'll be choosing between, let's do green. Because we'll do green for they're allowed. So we'll be doing this path is still allowed, and then this path is still allowed. So these are our two options. What's a path and array of points? Just want to remind that. And we'll probably end up choosing this path and then going across the same kind of strategy that we did when we didn't have a vehicle to worry about. So that's how a local path planner works. I'm sorry for my writing, it's pretty messy, but there you go. Now after this, your takeaway should be driving functions. We get inputs of the vehicle and the environment. We're outputting steering angles, throttle values, and braking values at every time step. Those are the control inputs for the vehicle. To do that, we're either using a global path planner, then a path follower, maybe some obstacle avoidance to get that strategy laid out, or we're just using a local path planner and figuring out the strategy that way. So those are the two schools of thought that I like to think about when I'm thinking about algorithms. Most likely what I've asked you to do if you're watching this video, or what another sub-team leader has asked you to do, is to watch this video, get a general overview of everything, and then kind of really zero in on the projects that you find most interesting from this. Like maybe look up another video on global path planning if you found that interesting, path following, whatever. So what I'd recommend, and I'm assuming your sub-team leader has already told you this, but after watching this, if anything really caught your eye, any algorithm you were super curious about, want to learn more about, look it up. A lot of this information is online on YouTube, which is the first place I like to go for general information. Then maybe start going into like research papers and more high level kind of topics or places to look. But I'd even look on YouTube for these ideas, and go to your next sub team meeting for driving functions with a way that you can go, like just information that you can go to your sub team leader with and be like, hey, I watched the video, I looked more into global path planning or local path planning, and I was really interested in this and this. I think I might want to pursue an algorithm in this type of area. What would you recommend I do next? So that's all you need to do right now. Just let this information sink in. This is all the basics that you're going to want to know before you start implementing anything anyway. So just if you can understand everything in this video, you're way ahead. Just take a deep breath and go to your next meeting with an open mind of an algorithm that you might be interested in as it relates to these different types of things that I've shown you. And I wish you guys all luck on creating one of these types of algorithms. It's easier than you might think once you get started. And yeah, good luck to all of you.